to this video. Today we're going to today we're going to do this. So this will define the zeta function at n as the infinite sum as s goes from 1 to infinity of 1 over s to the n, which is 1 over 1 to the n plus 1 over 2 to the n plus 1 over 3 to the n all the way on to infinity. And there is the famous basel problem, which was find zeta of 2, or 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared and so on. And I did a video on that, which showed it's equal to pi squared over 6. And today we're going to do it even more generally and find zeta to n for all natural numbers n. So the first thing to do in these kinds of find this for all natural numbers n is sometimes you want to look at the sum of this, zeta to n, times x to some power of n, x to the n, x to the 2n. Here it's going to be comfortable to use x to the 2n. And we'll try to work this to get some a sum that we can work with, and then so that will be like an identity we'll use later on. So this we can write as, by the definition of zeta, we have this is the sum as s goes from 1 to infinity of x to the n over s to the 2n, so that x over s to the 2n, and I will swap the sums. So I have sum as s goes from 1 to infinity of the sum as n goes from 1 to infinity of x over s to the 2n. But now this is a geometric series where the first number is x squared over s squared, the first term, and the r, the number we're multiplying by each time, is also x squared over s squared. So this is the sum as this goes from 1 to infinity, x squared over s squared over 1 minus x squared over s squared. Then just multiply by s squared, numerator and denominator, to get that this is the sum as this goes from 1 to infinity of x squared over s squared minus x squared. So now we have this sort of identity, and we will use it later on. So now let's try to think back to how we first solved the basel problem. In the video I talked about how we can express sine x as a product of x minus each one of its roots times some constant. And we got eventually that it is 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared, and so on, which is x times the product as n goes from 1 to infinity of 1 minus x squared over pi squared n squared. And what we did to solve the basel problem is look at the component of x cubed after we factor this out, and we looked at the Taylor series of sine x, and we got, after multiplying by negative pi squared, that it's equal to pi squared over 6. But what we're going to do here instead is try to evolve this. So first thing I'm going to do is replace x with pi x, just to make things a bit more simple here. So I have sine pi x is equal to pi x times the product as n goes from 1 to infinity, 1 minus x squared over n squared. Now what we're going to do, since infinite sums, since we have a lot more tools with to deal with infinite sums rather than infinite products, we're going to transform this into an infinite sum by doing a natural log on both sides. So we have natural log of sine pi x is equal to natural log of pi x plus, now natural log of the product is the sum of the natural logs. So this is the sum as n goes from 1 to infinity of natural log 1 minus x squared over n squared. Alright? Now we have that this function is equal to this function, and a very basic operation to do on functions is the derivative. So if we differentiate both sides, we get that here we'll have the derivative of sine pi x, which is pi times cosine pi x, divided by sine pi x, and cosine divided by sine is cotangent, so this is pi cotangent pi x. This is equal to, now the derivative of this is pi divided by pi x, which is 1 over x, plus the sum as n goes from to infinity. Since the derivative of the sum is the sum of the derivatives, we'll have this, now we need to take this derivative, and this is going to be minus 2x over n squared, which is the derivative of the inside, divided by 1 minus x squared over n squared, so over 1 minus x squared over n squared. And now I'll multiply by n squared and take the negative 2 out to get that this is 1 over x minus 2 times the sum as n goes from 1 to infinity of, we have x over n squared minus x squared. Now we will multiply by x to get, I write it here, so pi x cotangent pi x, and here we'll have 1 after multiplying by x, so I'll move it to the other side. Minus 1 is equal to negative 2 times the sum as n goes from 1 to infinity. Now after multiplying by x, this x turns into an x squared over n squared minus x squared. But we saw that this sum, n and s doesn't matter, it's just that parameter we're doing the sum over, so this sum is obviously this sum, which we found out is this sum. So this is negative 2 is the sum as n goes from 1 to infinity of zeta 2n x to the 2n. So now if we find a way to expand pi x cotangent pi x into some sort of infinite series, like Taylor series or something, then we'll be able to take the 2nth term of the coefficient of x to the 2n and say it is equal to negative 2 times zeta of 2n. So let's begin. So let's clear the board and look at pi x cotangent pi x. Okay, now let's try to turn this into an infinite sum. So we know cotangent is cosine over sine. And now we have cosine and sine and some pi's sprinkled around. It seems like we should use the imaginary formulas for cosine and sine, which I'll write up here in case you forgot. Cosine x is e to the ix plus e to the negative ix over 2, and sine x is e to the ix minus e to the negative ix over 2i. So now this is pi x times e to the I pi x plus e to the minus I pi x divided by e to the I pi x minus e to the negative I pi x. And then this is divided by 2 and times 2i. And so this is just times I. So I'll just write it as pi xi. Now I'll multiply by e to the I pi x on numerator and denominator. And I'll get pi xi is equal pi xi times e to the 2i pi x plus 1 divided by e to the 2i pi x minus 1. Now I want this to be something over e to the something minus 1, and a number divided by e to, in this case, 2i pi x minus 1. And so what I'll do is say this is this is 1 plus 2 over e to the 2i pi x minus 1. So I can say this is just minus 1 plus 2. And then this turns to 1 plus 2 over this. So I have 2 pi. I have pi xi plus 2 pi xi over e to the 2 pi xi minus 1. Now, let me quickly say z is equal to 2 pi xi, so we can see this better. This is pi xi plus z divided by e to the z minus 1. Now this has a famous expansion, which I'll also write here, x to the over e to the x minus 1 is the sum as n goes from 0 to infinity of the Bernoulli numbers over n factorial, where the Bernoulli numbers, if I remember correctly, go 1, negative a half, 0, 1 over 6, 0, negative 130. If I remember correctly, that's how they go. And so I'll just use this. This is going to be pi xi plus the sum as n goes from 0 to infinity of the and this is times x to the n. So I'll have z to the n, which is 2 pi xi to the n times the nth Bernoulli number over n factorial. Now, it turns out that this is the 0th Bernoulli number, this is the 1st, 2nd, 3rd, 4th, 5th, and it turns out from 3 onwards, 3, 5, 7, 9, 11, and so on, those Bernoulli numbers are all 0. B3, B5, B7, B9. And so, I can just say this is on the even sum, and when we're adding the term where n is equal to 1, because that's the only odd number which its Bernoulli number is not 0. So this is pi xi plus, when we plug in 1 here, we get 2 pi xi times the first Bernoulli number, which is negative a half, divided by 1 factorial, and plus another sum, but we can already see 2 and 2 cancels out. We'll have negative pi xi, because the sum of factorial is just 1, and pi xi and negative pi xi cancel out. Which is good, because we now got rid of the imaginary part, and it means that, and the rest of the sum will be real, because now we have sum as n goes from 0 to infinity. Now we're looking at only the even numbers, so we're replacing n with 2n, and we'll have 2 pi to the 2n times x to the 2n times I to the 2n, which is negative 1 to the n, times the 2nth Bernoulli number, divided by 2n factorial. This is pi x cotangent pi x. And now we know this is 1. We know that this is 1 minus 2 times the sum as n goes from 0 to infinity of zeta to n x to the 2n. So let's copy this sum. And before that, notice when we're doing a minus 1, we're actually getting rid of the 0th term here. And when we plug in n is equal to 0, we get some things to the 0, which is 1, divided by 0 factorial, which is 1, times the 0th Bernoulli number, which is 1. So all in all, the 0th term is 1. Minus 1 means that we can just start from 1. So this sum is just this, but it starts at 1 instead of 0. So we'll have the sum as n goes from 1 to infinity of, right, it is 4 to the n, pi to the 2n, negative 1 to the n, the 2nth Bernoulli number, divided by 2n factorial times x to the 2n is equal to negative 2 times zeta 2n x to the 2n. Meaning that I can just divide by negative 2. So this turns to negative 1 to the power of n plus 1. And we have a 2 in the denominator there. This is the sum as n goes from 1 to infinity of zeta 2n x to the 2n. And now, just like we said in the beginning, the coefficient of x to the 2n must be the same in both of these sums. And so we get our final result. Zeta of 2n is equal to negative 1 to the n plus 1 times 4 to the power of n times pi to the power of 2n times the 2n Bernoulli number divided by 2 times 2n factorial. And if you don't believe me, you can check for yourself. Let's try to plug in n is equal to 1. In that case, that will be the basel problem, the infinite sum of the inverses of squares. That will give us negative 1 to the 2, that's 1, times 4, so, alright, this negative 1 to the 2 times 4 times pi squared times the second Bernoulli number, so 0, 1, 2, it's 1 over 6, divided by 2 times 2 factorial, which is 4. This is 1, 4 cancels out, we get pi squared over 6. And just to check again that this isn't a fluke, let's 6, not 60. So let's check if this isn't a fluke. Let's try zeta of 4. The inverses of powers of 4. This should be pi to the 4 over 90. And we have negative 1 to the power of 2 plus 1, which is 3, times 4 squared, which is 16, times pi to the 4th times the 4th Bernoulli number, which is 0, 1, 2, 3, 4, negative 1 over 30, divided by 2 times 4 factorial, which is 48. 4 factorial is 24. This goes with this, and we have 3 left at the bottom. The negative 1 to the 3 is negative 1, which cancels with the negative and the minus 1 over 30. 30 goes to the denominator, and we'll have pi to the 4 over 90. And if you continue on, you get that these infinite sums, and if you actually check, these are the infinite sums. And this is the solution. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.